Hello and welcome to today's episode of Beyond the README, where we're going to be talking about load balancing and the impact it has on client IP addressing. Load balancing is a personal favorite topic of mine because it's a key component of running robust web services, and there are lots of subtleties that people often don't think of, or they might be vaguely aware of them but unsure of how they really work under the hood. And I think client IP addressing is a great example of that. In this video, we're really going to dig into what happens to a client IP address as it traverses different kinds of load balancers so that we can understand the impact that load balancing has on client IP addressing and understand how to properly access client IPs in our upstream web servers. So first, a little bit of background. You've probably seen some articles or read a tutorial about how to configure a load balancer to properly pass a client's IP address to a back-end web server. You may have seen some articles about the X-Fowarded-For header or the X-Real client IP header or things like that. But why do we have to do this? What's actually going on under the hood at the network and packet level that forces us to make these configurations? How do those considerations change across different types of load balancing strategies? Do we have to consider things differently if we're using a TCP versus an HTTP-based load balancer, and why? And finally, why do we care about this at all? What difference does it really make, and what are some of the special considerations we need to have? So first, the why. So you're probably aware that a load balancing strategy can impact the way traffic is presented to an upstream server. IP addresses can and often do change when you place a load balancer between your client and your servers, and this impacts the visibility that those backend servers have into the original traffic. Depending on the load balancing strategy in use, there are different ways to ensure that we can still pass that real client IP address to the backend server. This method is going to depend on the type of load balancing in use, and you're going to see that today. And finally, why should you care at all? Knowing the real IP of a client is very important for things like security, logging, or performing different kinds of actions based on the geographic location of your user's traffic. It's also very important to understand how to configure a backend application to process traffic coming from a load balancer. I've seen many examples of misconfiguration where a backend web service doesn't actually have visibility into a client's IP address because it's not configured properly. A great example of this is NGINX. You need to make a change to the log format when you place NGINX behind an HTTP-based reverse proxy. So let's start with our environment setup that we'll be using to conduct some different experiments and look at traffic. I have a fairly simple topology here with a client that is representing an internet-based client, a load balancer that exists in a front-end and a back-end network, so it has two interfaces, one on each network, and then a back-end web server. In this case, my load balancer will be HAProxy and the built-in Linux IPVS, the IP virtual server load balancer, and my back-end web server is NGINX. I'm deliberately not using a cloud provider's load balancing technology here because I want you to understand the fundamental underlying concepts, and we're going to do that by looking at packet captures and logs so that we really gain an understanding of what the traffic looks like. If you can understand these underlying concepts, then you can extrapolate them to any cloud vendor or any technology that you want. So let's start with what is probably the most common type of load balancer in many environments, and that's the HTTP or HTTP-based reverse proxy. In this case, a client establishes an HTTP connection to a load balancer, and then the load balancer establishes its own HTTP connection to a backend web service. So in this case, there are actually two HTTP or HTTPS-based connections, and the load balancer is effectively man-in-the-middling that traffic. It takes the request coming from the user and sends it to the backend web server on its own connection, and then it receives that response from the backend web service and passes that to the user. These are two separate HTTP or HTTPS connections. So in this case, I have that NGINX web server running, and I can see it's just presenting a default NGINX page, and that will be sufficient for our experimentation purposes. I have my load balancer configured to use HAProxy with a fairly simple configuration. I'm listening on port 80 on my front end, and I'm sending my traffic to the single backend web server that we have, and this will perform HTTP-based reverse proxying. So let me open up my client and send a web request to the front-end IP address of the load balancer. This would be the IP address that you would present to your upstream clients, and the load balancer would handle distributing that load to the backends. And we can see here that my request came in to 192.168.100.100, which is the load balancer's IP, and that was forwarded back to the backend NGINX server. Now let's take a look at the log file on that NGINX server. So here I'm printing out the last two requests to my NGINX server. We can see the one that came from localhost, and then we can see this request that we just sent. And what you'll notice is that the IP address listed here is the IP address of the load balancer. Going back to our topology view, the IP address that the web server is seeing is this backend IP address 192.168.200.100, and that is the IP address of the load balancer's backend interface. So it never sees the client IP address. And so the client IP address does not end up in the log file. So let's take a look at why that's the case. Let's perform some packet captures on both our load balancer and our web server, and then analyze them to understand what the traffic looks like. So I'm going to start up a packet capture here to capture port 80 traffic on my load balancer, and I'm going to do the same thing on my web server. With these packet captures running, I'm going to resend my request from my client. I'll go ahead and end my packet captures, and we'll pull them up in another window to analyze them. Okay, I have my packet captures here, one in each window, one for my load balancer and one for my web server. And let's take a look at the HTTP traffic. So we're going to ignore the TCP three-way handshake for now. I'm going to assume you're familiar with that. We're going to focus on the HTTP traffic itself. And so let's first take a look at our source and destination addresses at layer 2. In this case, my source address ends in BE71 and my destination ends in 24C5. And if we come back to our topology, that matches the front-end gateway as the source address, and the front-end interface on my load balancer is the destination address. So this is information that is traversing a router and coming in from my default gateway and being sent to my load balancer's front-end IP address. Likewise, if we take a look at the IP addressing, we'll see that the source address is the client's IP address, that 172 address, and the destination is the front-end IP address on my load balancer. Now if we head over to the web server, let's take a look at the traffic that it sees. So in this case, it has an HTTP GET request. And if we take a look at that layer 2 addressing, we'll see that our source address ends in A710, our destination address ends in 66BA. And in this case, A710 is the backend address of our load balancer, and 66BA is the address on our web server at layer 2. So this is traffic being sent by the load balancer. This is the back half of that connection, the connection from the load balancer to the web server. And similarly, if we look at our IP addresses, we will see the same thing. The source address is 192.168.200.100, which is the back-end interface of our load balancer, and the destination address is 192.168.200.101. So let's review what this flow looks like on our diagram. My client comes in from the internet and connects to that front-end load balancer IP address. The load balancer establishes a connection with my client. On the back end, the load balancer establishes a separate connection with the web server. So these are two different connections, and in this case, the addressing for that back-end connection uses the addressing from the load balancer, which makes sense. In this case, the load balancer is the initiator and receiver of that traffic to the web server. So in this case, our original client address is lost because we have two separate connections. From the web server's perspective, the client is the load balancer. So let's see how we can pass a special HTTP header to indicate to our web server that a load balancer exists in the path and is forwarding traffic on behalf of our client. The common way to do this is with the HTTP X-Fowarded-For header, and I can add that to my HAProxy load balancer very easily. By specifying the forward for option to HAProxy, it will append an HTTP header with the original client's IP address in the X-Fowarded-For header. I'm going to make that change and restart HAProxy. Now if we come over to our web server and we tail out the log file, we can see what the traffic looks like. So I'm going to send another request from my client, and now we see that the IP address is actually still the same. This is still the load balancer's IP address. And that's because NGINX has to be configured to log the X-Fowarded-For header. This is a very common thing when you have a load balancer in front of software. You need to make sure that your software is aware of that load balancer and any headers it's sending. The configuration is going to, of course, vary depending on what software you're using, but you have to keep in mind that your backend software needs to be configured. This is a very common issue that I've seen in my experience. Folks will forget to configure their backend software or logging, and then when they go to troubleshoot an issue, all the IP addresses they see in their logs are just those of the upstream load balancer. So I'm going to head over to my NGINX config file, and I'm just going to set up another log formatter. And in this case, without getting into the specifics, because they're not necessarily relevant to the concepts, I'm just having NGINX log that X-Forward-For header, as well as the remote address, and then the rest of the request. I'm going to adjust my access log to use this new log formatter. Now I'll restart NGINX, and we'll take a look at that log file again. Now when I send my request from my client, we can see the client's original IP address, and we can see the IP address of the load balancer. So NGINX is now configured correctly to receive that information coming from the load balancer. Let's take a quick look at another packet capture that I have that shows what's actually going on here. I've once again got the same packet capture that I had previously, one for the load balancer and one for the web server. If we take a look at the original HTTP request coming from the client, we'll see that we have some of the common headers, host, user agent, things like that. But now if we take a look at the GET request that the web server is receiving, we'll see the addition of the X-Forwarded-For header, and that has the real client IP address in it. So even though the load balancer is establishing two separate streams, when it sends that stream to the backend or upstream web service, it adds this header so that that upstream service knows who the original client was. Now, X-Forwarded-For is a common header. You will also see others like X-Client IP or X-Real IP. They're just HTTP headers. The name itself doesn't really matter, although we typically stick with the common one of X-Forwarded-For. And if there are multiple proxies in the path, they may also add their own IP addresses to that header. So now you've seen how all of this works with an HTTP-based reverse proxy. Again, as a reminder and in table format, in this case, our client sends traffic to the load balancer. At layer 2, that load balancer receives the traffic from its router or upstream gateway. It can see the original client IP address. It then establishes another HTTP connection to a backend or upstream web server. And in order for that upstream web server to know about the original client's IP address, we need our load balancer to add a special header. So let's briefly discuss some special considerations when it comes to this approach. First, anyone can set an HTTP header. This can lead to issues like X-Forwarded-For spoofing, so it's very important that you trust the header has been set by your upstream proxy. Again, many pieces of software have the ability to control what proxies they trust upstream. Additionally, lots of proxy software can strip a header before forwarding it on to a client. So you might consider stripping the X-Forwarded-For header at your proxy if it has already been set, especially if you don't expect any other proxies to exist in the flow between your client and your backend web service. As I mentioned, backend software can be configured to trust proxies, and that is usually a good idea, especially if you're using any of that data in the headers for special decision making. And in many cases, it's a good idea to actually filter at the IP layer, like with a firewall or IP tables, the traffic between your web server and the upstream proxy, so that only that proxy, that load balancer, can talk to that backend web service. So that gives us an overview of load balancing and proxying at the HTTP layer. But what if we move one layer down the stack and look at TCP-based reverse proxying and load balancing? So this is very similar to HTTP-based reverse proxying. The only difference is that our load balancer isn't acting at the HTTP layer, it's acting at the lower TCP layer, which can often be used for performance. Because the load balancer doesn't have to process as much of the packet, it can be more performant. So let's start by adjusting our load balancer to switch to TCP mode and remove the forward-for header since it's not going to have relevance for us in this case. And you'll see what I mean by that in a second. So now when I restart my load balancer, it's going to be performing TCP-based reverse proxying. Now if I head over to my client, I can still access my web service. But if I take a look at my NGINX log file, you can see that I no longer have the client's IP address. And this makes sense. The X-Forwarded-For header is only relevant if we're doing HTTP-based proxying. A load balancer that's operating at a lower level of the stack obviously is not going to insert that HTTP specific header because it's not performing analysis of that upper payload inside of the traffic. And this is also true of traffic that doesn't support X-Forwarded-For, so non-HTTP based traffic. You might be proxying some application specific TCP traffic that obviously isn't HTTP based, so there's no way for you to leverage the X-Forward-For header in that load balancing strategy. So we have to come up with another option to gain visibility into the original traffic here. In this case, there's an excellent protocol called the Proxy protocol that's able to work with any TCP-based connection, and it effectively works by inserting some data into that connection to provide the original client's IP address. The Proxy protocol is pretty widely supported by common software, including NGINX in our case, so we can still leverage the information even though we're not going to be working with an HTTP header. So let's start by configuring our load balancer to send Proxy protocol information. And let's just start there and see what happens. I'm going to restart HAProxy and retry my client connection. And now we get this 400 bad request. And when we're going to take a look at the packet capture in a few minutes, you'll understand why this is. But for right now, we just have to understand that we need to configure our upstream software to be aware of this proxy protocol. So in NGINX, we can configure this at the virtual host level. So if I open up my default configuration file, I have my listeners, and I can instruct them to accept and be aware of the proxy protocol. Just like we saw with the forward-for header, we need to make our logger aware of this new information. So I'm going to use a different log format here, and now I'm using the proxy protocol address variable to log that address. And we'll update our access log to use that log formatter and restart our web server. Now let me retry my client request. Now I can see my client request succeeds, and if we take a look at our log file, we'll now see the client's IP address as well as the load balancer's IP. So it's now processing the proxy protocol correctly. So from a layer 2 and layer 3 addressing perspective, the Ethernet and IP addresses, we haven't really changed anything here. Instead of looking at the HTTP payload, our load balancer is simply performing at the lower layer of TCP. So our addressing is going to be the same. But let's still take a look at a packet capture that I have that demonstrates what the proxy protocol looks like. So I once again have a packet capture from my load balancer and from my web server. Now let's take a look at the original client GET request. We can see the source and destination IP are exactly what we would expect. The client's IP is the source and the load balancer is the destination. You can also see this came in on source port 48,494 and is destined for port 80. The web port. The HTTP headers are exactly what you would expect, no changes there. Now let's head to our web server and take a look at what it sees. We have our TCP three-way handshake, and now we have this interesting packet right here. Wireshark interprets this as an HTTP packet, but it's actually the proxy protocol information. So if we expand the actual data that's in here, you can see the base 64 encoded payload. Let me go ahead and copy that as printable text so we can see what it actually is. If I throw this into a text document, we can see this is actually the proxy protocol header. So after the three-way handshake, our load balancer is inserting some special data into the stream that contains information about the proxying. And this should look pretty familiar. The proxy indicates it's the proxy protocol. We're using TCP version 4 because remember we're operating a TCP-based load balancer. And then we have our client IP address, the destination IP of the original packet, as well as the original source and destination ports. So all of that information is encapsulated and our backend service can be aware of it. And then we get our HTTP GET request, and again you can see clearly that there are no special headers in the HTTP payload. The load balancer is working at a lower layer of the stack. So just to review this on the diagram, now my client establishes a TCP connection to my load balancer, and my load balancer establishes a separate TCP connection to my web server. My load balancer doesn't consider the HTTP payload at all. In fact, it has no idea what the traffic in that upper layer protocol is. This makes TCP-based load balancing fairly performant, since none of that higher level application data needs to be analyzed. And this is fundamentally how things like AWS network load balancers work to deliver very high performance. So let's take a look at some of the special considerations that come along with TCP-based load balancing. So first, just like HTTP reverse proxying, we need to trust that upstream proxy. In this case, IP filtering is certainly a good idea, and that ensures, just like with HTTP-based load balancing, that only the proxy can send traffic to the backend. One consideration that you might have is that the proxy protocol support might be limited in your application or the library you're using. The proxy protocol is pretty widely supported, but it's obviously not as simple as an HTTP header. But the benefit here, of course, is that you can use the proxy protocol with non-HTTP traffic. So far, we've been looking at load balancing and proxying strategies that establish two connections. The client establishes a connection with the load balancer, and the load balancer establishes a connection with the backend service. Another type of very powerful load balancing that you might come across is transparent load balancing. Transparent load balancing is supported by a variety of vendor software and hardware, but it's also supported directly in the Linux kernel with something called the Linux virtual server. So in this case, the traffic is going to look quite different, and we're going to see what that means. The configuration for IPVS or IP virtual server is a bit esoteric, but fundamentally what we're going to be doing is having our load balancer act like a router. The original client IP address is going to be preserved in the packets sent to our upstream web service. So first I'm going to stop HAProxy because we're not going to be using that anymore. And then I'm going to configure the IP virtual server. What I'm fundamentally doing here is enabling IP forwarding and then configuring a special IP virtual server to listen on the front-end IP address of 192.168.100.100, port 80, and then forward any traffic transparently to my back-end service, which is the web server. And I can see my virtual service here is configured correctly. The configuration on the back-end web service is a bit more complex. I similarly need to enable IP forwarding, and I'm going to enable ARP ignore as well just to be safe, because what we're actually going to do is configure the front-end load balancer's IP address on the back-end web server's loopback address. So the original traffic is going to be presented to the web server in the same way it's presented to the load balancer. So in this case, I'm actually adding that same front-end IP address that the client accesses to the loopback interface of my back-end web server. and I'm adding a route to send any traffic destined for that address to my loopback. So now if I look at the addresses on my web server, you can see that it actually also has that IP address that the clients are going to access configured on it. Now going back to our topology, you'll know that this address isn't really accessible from that network that this web server is on. They're on different networks. But with this configuration, we can actually pass the original IP packet to our backend web service. So let's actually see what this looks like. First, we need to disable the proxy protocol support in NGINX since we're not using that anymore. Then I'm going to restart NGINX. And I'm going to head over to my client and send a request. And we can see the request succeeds. Now let's take a look at our log file. You can see we're actually getting the real client IP address here. These blank fields are caused by the log formatter we're using. So let's just switch back to NGINX's default log formatter. And now if I send a request and take a look at the log file, we can see the original client IP address. So what's actually going on under the hood here? Well, in this case, we have to actually take a look at a packet capture to really understand what transparent load balancing is doing and understand why the original IP address is present. So now I once again have a packet capture for my load balancer and my web server. Let's start with the load balancer. This is probably becoming pretty repetitive. We've got our original packet, our source and destination addresses are the load balancer's default gateway destined to the load balancer, and then my source IP address is the client's IP and the destination is that 192.168.100.100 address that the client is accessing. My HTTP headers look totally normal. If I head over to my web server, this is where it gets kind of interesting. If we look at the GET request, we can once again see the source and destination MAC addresses are coming from the load balancer. But what's really interesting here are the source and destination IP addresses. Notice that the source address is exactly the same as the client's IP, 172.16.10.242, and the destination address is also the original IP address. So we don't have two connections here. There's nothing interesting going on in the HTTP headers either. So in this case, our load balancer is passing that IP packet unmodified to our backend service. Where it also gets interesting is taking a look at the return traffic. So if we look at the return traffic that's being sent to the client, the source Ethernet address is the interface on our web server. It's destined to the web server's default gateway, not the load balancer. Similarly, the IP packet is the same. The source IP address is the original IP address that the client tried to access, and the destination IP address is the client's original IP address. So the client has no idea in this case that it's talking to a load balancer at all. Our load balancer is transparently forwarding that traffic at the IP layer to the backend service. So in our previous examples, we had two connections, but in this example, we have one single TCP HTTP connection to our backend web service. Our traffic comes from our user to our load balancer, and then it goes through the load balancer to our backend web service. The web service then responds directly to the client, bypassing the load balancer entirely. It goes to its default gateway, and that traffic eventually ends up back at our end user. So our load balancer is fundamentally just dispatching the packet to where it needs to go, and then the web server sends the traffic back to the client directly. Because all of the IP addresses are the same, this ends up working just fine. The client has no idea that it's talking to a load balancer or that it's talking to the backend web server. It's none the wiser. Similarly, we can get very high performance out of our load balancer because it doesn't need to establish two connections. It effectively just receives the packet, dispatches it accordingly, and then it leaves the rest of the traffic up to that backend service. Transparent load balancing can be an important aspect of highly performant load balance services. So once again, we have that one TCP connection from our client to our backend web service instead of the two TCP connections that we've seen previously. And again, just to really drive this point home, here's a table with all of the addresses in it. Notice that the IP addressing remains consistent across the entire connection. Also notice that the upstream web server responds directly to the client by means of its gateway, and there is no load balancer to client traffic because the return traffic is not handled by the load balancer. Now there are some special considerations with transparent load balancing. As you may have noticed, there is an asymmetric routing problem here. The traffic coming to the web server follows a different path back to the client. That can sometimes be a problem in certain environments and is certainly worth being aware of for troubleshooting purposes. Transparent load balancing can be kind of challenging to troubleshoot. However, it is often extremely performant. So over the course of this video, you've had the opportunity to look at three different load balancing and proxying methods: the HTTPS or HTTP reverse proxy method, the TCP reverse proxy method, and the transparent load balancing method. Each of these provides a different set of benefits, and each has a different impact on how the traffic is presented to the upstream web service, which of course impacts the way that upstream service sees the client's original IP address. All three of these are components of a robust load balancing strategy, and you should be aware of and understand their limitations and features. Hopefully, by taking a look at the packets and the actual traffic, you developed a deeper understanding of how these different load balancing technologies work and what things like the X-Forwarded-For header actually are. Thank you so much for joining me on this episode of Beyond the README. If you enjoyed this episode, be sure to like it, subscribe, and share it with your colleagues. I'd really appreciate it. I'll see you on the next episode.